Okay, so today we'll be going through MAT 2022, and as usual, I'll start by going through the problems. Okay, so this is basically I'll be going through the first 5 problems as usual because that's for pure math students, and the rest are all like computer science or philosophy based. So the first 5 questions are the ones that sort of like do matter the most if you're applying to do math at Oxford, pure math at Oxford. The rest it's are like if you're doing a combination of things. Okay, so many real solutions like that to the equation. Okay, so first consider if one like x is greater than or equals to 0. That gives you x squared plus 1 equals to 3x. And so x is equals to 3 plus minus root 5 divided by 2, which is satisfies both cases. And in second case is when x is less than 0, you get negative x squared plus 1 equals to negative 3x, which gives you x squared plus 3x minus 1, and hence x is equals to negative 3 plus minus root of nothing divided by 2, and only one fulfills this condition that x is less than 0. So there are a total of 3 solutions for the first question. Okay. For B, 100 circles share the same center. They are named. Okay, so you can kind of imagine that it looks something like this. The center here, and then the circle that's slightly bigger. So this is one, and then this is the radius of the largest circle, which is Rn plus 1. And this is the radius of the small circle. And so you get Rn plus 1 squared equals to Rn squared plus 1. And so like basically governed by this equation, you have like R squared of 100 equals to a square root of 1 plus like 99, which is 100. And so the radius of this is 10. And so the answer is D. Okay, moving on. Okay, so usually equations of a circle complete the square. So we get like x minus 2k squared plus y minus 4, no, y minus 2 squared equals to k cubed minus k plus 4k squared minus 4. And so essentially you must have this equals to some r squared, which is greater than or equals to 0. And you complete the square, k squared minus 1 plus 4 k squared minus 1 larger than or equals to 0. K plus 4 times k squared minus 1 is larger than or equals to 0. And so, well, like it's a cubic equation, and you have the solutions at like k minus 1, k plus 1. And so it all looks like this. And then you know that when k is less than negative 1, like take for instance like negative 2, well, like negative 4, 1, negative 1. So if k is like at negative 6, then it's negative. So it's all like this. So when is it greater than or equals to 0? It's when k is greater than 1, or negative 4 less than k less than negative 1. And so the answer is B. Okay, moving on. D. So for this thing over here, you try the small cases first. You realize that A1 is equals to 8 times 3 to the power 4. And then, so this is like 2 to the power 3 times 3 to the power 4. And A2 is equals to 2 to the power 3 times 2 to the power 12 times 3 to the power 16, which is 2 to the power 15 times 3 to the power 16. And so you sort of do realize that, oh, the power of 2 is always 1 less than the power of 6, the power of 3. And so like A10 will be equals to, since this is like 2 squared, and this is like 2 to the power of 4. And for A3, it's gonna be 2 to the power 60 times 3 to the power 64 times 2 to the power 3, which is equals to 2 to the power 63 times 3 to the power 64. And here it's like 2 to the power 6. And so at this point, it will be 2 to the power 20 minus 1 times 3, 2 to the power 20. And so this gives you 6, 2 to the power 20 divided by 2. And so the answer is E. Okay, moving on. Okay, well, so you can sort of break it up into like binomial terms in this form, whereby it's like x plus whatever x to the power 4 plus 4 1 x plus whatever x to the power 3 plus 4 2 4 3 x plus 1 plus x plus 4 4. And like the other terms whereby the coefficient of x is equals to 0, and you know that for the odd terms it will always have like an odd coefficient, so it can't be 0. And so it leaves you to consider these few cases. And so there's like 6 times 2 here, which is 12. There's 1 here. And then for this case, it's x to the power 4 plus 4 1 x squared plus 4 2. And so this is 6. And so adding everything up together, you get 19. And so the answer is C. Okay, moving on. Okay, so you have theta equals to 72, which gives you 0 equals to 5 sine 72 theta minus 20 sine 72 theta cube. I mean, well, for simplicity's sake, can let this be x. So equals to x 5 minus 20 x squared plus 16 x to the power 4. And you factorize, and this gives you 4x squared minus, would you factorize it? I don't think so. Okay, so well, the x itself clearly can be equals to 0. So you must have like 16 x to the power 4 minus 20 x to the power 2 plus 5, which gives you x squared equals to 20 plus minus 400 minus 320, or just 80 divided by 32, which is 5 plus minus 5, 8. And since it's between 0 and 1, so it has to be positive. And okay, well, so you check out C, you check out E, so you're left with A and D. But then you know that this also has to be greater than sine 45, which is 1 root 2, and clearly D is the smaller of the two, so the only possible one is A. Okay, so mm, it's like n to power 4 plus 2n squared plus 1 minus 2n squared. Okay, so for g, you still realize that it's n to power 4 plus equals to n squared plus 2 squared minus 4n squared. And so this gives you n squared plus 2 minus 2n, n squared plus 2 plus 2n. And so it can't be a prime number, like, because the sum of the two terms is this one, and when you have this one equals to 1, it gives you n squared minus 2n plus 1 equals to 0, and n equals to 1. I mean, okay, it can be the prime number for n equals to 1. And I think that that's the only case. And other than that, it has a composite. It's composite because it has a prime factor. Okay. And for this one, 2x cubed plus 7x squared plus 2x plus 3 gives you x cubed plus 3x squared plus 3x plus 1 times 3. So your 3x squared, x cubed plus 9x squared plus 9x plus 3. And so it's like 2x squared plus 7x equals to 0. And the number of real solutions is thus 2. Yeah. Hmm. At least wins if, okay, at least wins if strictly more of a constant heads than what quants do. And we call probability P1. Okay, and um, but, I mean, theoretically speaking, P1 should be 2P1 plus P2 equals to 1, and that should be true regardless of because there's a symmetry in this problem. So, well, if you check for this, 193 times 2 equals to 286 plus 126. Oh, which also gives you 512. Oh, I think perhaps most of their solutions do fulfill this condition. Yep. So it'll be like 2P1 plus P2 equals to 1 in general. And so basically a number of heads that at least gets equals to the number of head that Bob gets for all the 5 bank coins. You can just calculate P2 to get what P1 is. And P2, well, you have like 5 choose 2. It's like probability of them getting like 5 0 heads and um 1 head and then 2 head and like and so on. And this gives like 63 over 63 possibilities, and you divide it over 256. And so this gives option A. Okay, moving on. Well, for these two equations, then like the most logical thing for you to do is to sub both in, sub both in and see what you get. So you have like x squared plus m squared x squared plus 2m xc is c squared equals to x squared minus 6x plus 9 plus mx squared plus c squared plus 1 plus 2mxc minus 2c no, minus 2mxc, plus 2mxc minus 2mx. And so you cancel some away, cancel this, cancel this, cancel this, and well, you get like 2c equals to 9 minus 6x minus 2mx. So how many possibilities are there for the line here? Okay, well, like now we look at it the graphical way and you realize that this is like a circle and this is another circle and they don't necessarily cross each other. And so if they have a repeated root, that means that there exists a tangent somewhere. And so you can just basically draw like a common tangent to both of these, which looks something like this. And they ask like what's the possibility of like y equals to mx, which is like another tangent that has a different like gradient, but also is a tangent to both of these circles. So it's another one here, another one here. And so total will be like 4 lines that's both tangent to these circles. So essentially they're asking for like common tangents down to these circles that like have on the same line. So it's like 4 of them. Okay, so I mean, looking at this immediately reminds you of like the Pell's equation, and that's like something that's more the Olympiad level. The Pell's equation, which is something more on the Olympiad level. Okay, but essentially, it's also like using the idea of a recurrence to get your desired solutions in. So you expand this x4 plus 2nx squared y squared plus n squared y cubed y4 minus 78x squared y squared equals to, do you want to show that it equals to x to the power of 4 minus 38x squared y squared plus 361 y to the power of 4, because this is like c squared. And so you choose what n has to be. So you compare coefficients on both sides. You have n squared equals to 361. So n is equals to 19. And you check for x squared, y squared, and it works. So n is equals to 19. Okay. And now they want you to find z of x is equals to 13 and y is equals to 3. So you sub it in. 169 minus 19 times 9, 8. 169 minus 19 times 9 equals to 171, which is -2. And so here you have find a pair of whole numbers x, y with this thing true and x greater than 2. So here you have x squared minus 19y squared equals to -2. And so x squared plus 19y squared minus 19 2xy squared equals to 4. And so you sub in this x, sub it with like this thing here, which is 13 squared plus 19 times 3, giving you 169 plus 171 equals to 340. And the other one is y, which is 2xy. and that gives you 78. And so the two solutions are like 3, 4, 0, and 78. Okay, so, well, I mean, immediately you sort of realize that they do have a common factor of 2 for the next part. And so pretty simply, you can just divide it by 4. It's like 170 and 39. Is your solution the only pair of positive numbers? No, because like if this is like x1 and x2, if this is like x1 and x1, then you can use this equation here to get x2 and y2, and so on. So it's definitely not the only solution. Okay, prove that there are no whole number solutions to this. Okay, so well, you have like x minus 5y and x plus 5y equals to 1. So like either this is -1, or this is like 1 and 1. Oh, which gives you y equals to 0 and x equals to 1. For both cases, and that doesn't work because the question wants you to get like x greater than 1. Okay, here they just want you to find like one positive uh, number that works. So x squared minus 14y squared equals to 1. So you have like, so you notice that 1 minus 17, 4 squared minus 17 times 1 squared equals to -1. So you can square this as well. And so the new x you get will be 4 squared plus 17 times 1 squared, which gives you 33. And then y is 2xy, which gives you 8. And so the solution is 33 and 8. Okay, I'll sketch the graph y equals to. So you notice for the one that gives you a square, it has to be always positive. So it's gonna look something like this with a symmetry about the y-axis. And then for the other one, the curve is slightly, or it's slightly more extreme. It's gonna have an inflection point at that point. And then, yeah, something like this. So this is the one with power 3, this is the one with power 2. Okay, without calculating the integral explicitly, explain why there's no, well, like what I said before, if n is even, it's always greater than or equals to 0. And then so the area has to be always greater than or equals to 0. And if it's like strictly 0, that means that and that means that a is equals to 0, which can't be the case because you want like something that's positive. So now if n greater than 0 is odd, then we write n equals to 2n minus 1. Okay, explain why such a number exists. Oh, because this is an odd number. So there's gonna be like area under the graph and area below the graph. Since like from 1 to 0 is x squared minus 1 to n minus 1 dx is less than 0, but then for something that's from like a to 1, it increases and without bound. So eventually it will be equals to 0. Okay, so now I want you to find what A1 is. A1 is 0. x squared minus 1 dx, which is x cubed minus x a1 is 0 equals to 0. And so x cubed 1 minus a1 equals to 0. a1, a, no, x divided by 3. So a1 squared equals to 3. And this gives you a1 equals to negative 3, root 3. Okay, I probably should erase everything because it gets a little bit complicated. Now they want you to find what a2 is. So it's a2, 0, I squared minus 1 to the power 3 dx equals 0. So this gives you a to the power 4 over 7 plus 3a to the power 5 over 5 plus a to the power 3 minus 1. And when a equals to root 2, this is negative. When a equals to negative root 3, this is positive. So by intermediate value theorem, this is to cross the graph of y equals to 0 at some point. So this is true. Now I want you to find the approximate new value of m when m is a very large whole number. So yeah, that from 0 to root 2, the integral is close to 0. The integral gets close to 0 if m is large. And it's negative from 0 to 1, and from 1 to root 2, it's positive. So you can kind of imagine that the integral up to root 2, like when this limit tends to root 2, it's still negative. But then when it gets greater than root 2, then it gets positive really quickly. So either ways, from both sides, it tends to root 2. Okay, sketch this graph and find the quantity of the turning point. So the graph will look something like this. Oh, across the origin, sorry, like this. And then you differentiate it. This is x half. So it gives you like, so x is equals to 4 and y is equals to 1. And that's the turning point for 4 and 1. Okay, this kind of works how the graph of this is related to the graph that you sketched earlier. And so you realize that if you let y equals to fx, then you set y equals to fx plus 1. It's going to give you something like root fx plus 1 minus fx plus 1 over 4. And then you translate it again by negative 3 over 4 to get this final graph here. So like, how do you get this then? So you basically sub in x, you sub in for x plus 1, and then you translate by negative 3 over 4. And so first you stretch by times 4 parallel x, and then translate by 1 over 4 to the left, and then 3 over 4 down y-axis. And so the coordinate now will be like 3 over 4 and 1 over 4. Okay, now I'm erasing everything. Okay, so there is gonna be a symmetry about the origin because that's the where the point is, and then the it takes the product from this point P to the 2 points. So there's gonna be a symmetry about the origin. And so um first you consider where this point P is left of A. So if x is -1, then it lies on the same it, it curves C. No, that's not. So it lies on the same, yeah, it's the x-axis. So right here is like P is here, and this is x, and then this is okay, well, you let this be x, and this is like x plus 1. So you get like 1 minus x, 1 plus x equals to 1. And so x is equals to -√2. And then this is the same thing for when it's y of x, so x equals to √2. And now you consider when it's like between everything, so it's like x squared equals to 1, which gives you the origin. And so the points are like √2, 0, -√2, 0, and 0, 0. Okay, so find a point in terms of find an equation. Okay, so well, if it's consider something that's like x, y, it gives you like root x squared, x plus 1 squared plus y squared times 2 x minus 1 squared plus y 1 squared equals to 1. And so you expand, you get a quadratic, you get like y to the power 4 plus 2 x squared plus 1 y squared plus x to the power 4 minus 2x squared. And since you want something that's real and positive, then you have like y equals to root 4x squared plus 1 minus x squared minus 1. And that's the only possible solution for y positive and real. Now you use the plot pad I to determine the coordinate of any turning point of the curve C in the region where x is greater than 0 and y is greater than 0. Okay, so the previous solution is like y equals to 4x squared plus y minus x squared minus 1. And so it's like taking a root of y, but then replacing the x with x squared. And so it's kind of gives you like you reverse engineer the previous solution, which is 3/4 and 1/4. This gives you √3/2 and 1/2. Okay, now they want you to sketch the curve. And so yeah, this is like √2. This is 0. This is 0/2, and then it's gonna look something like this with symmetry on both sides because yeah, there's a symmetry about the both axes. And so it's like -√2, this is +√2. Okay, now moving on to the last problem. Okay, so for pi it's pretty straightforward since like there's certain and there's some items, so you choose all the odd possible doors. So you can see like 1, 3, 5, 7, blah 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 until 13. Okay, for II, they want you to find for any form of 2k+1. So basically this is like the base case. And then for this onwards, it's like 1, 3, 5, all the way on to 2k+1. And briefly justify your answer. So like basically like you check every single door and then like check every single door afterwards and you realize that it does check for every single door before it. And so it does confirm like a new item for at least every single time. So all in all, it's like k plus one items. So this one basically asks you for any sequence of doors that Elise can pick. So Elise can pick like 1, 1, 4, 4, 7, 7, 10, 10, and 13, 13 for any plus of 13. So she can guarantee she wins 10 items. And that's because like if you swap around, like basically like having an interval of 3 between this ensure that you can pick up an item every single time. And also any permutation of this works. And okay, so similarly, they just do the same thing. They ask you for a small case, and now they want you for the big case. And like previously, there's like k equals to 4, and it's like k equals to 4 again. So it's like 1, 1, 4, 4, and then all the way until 3k plus 1 and 3k plus 1 as well. And they want you to like justify your answer. So basically, you realize that when you group the items in terms of like A3, A4, A5, A3k plus 1, A3k plus 1. So every single time a door from each group is picked, you realize the items itself are in their original position. And like each time for like every single door in the groups of 3, it's like in the middle. It's like in the middle. So she wins at least 2 items from each group. And then at the boundaries, she also wins like at least 1. So adding up everything together, I guess you win 2k plus 2. And all in all, there's like k plus 1 groups. Okay, for any question tree, give a sequence of 3 doors such that at least picks one that guarantees she wins all 3 items. And so like 1, 1, 3 works because if it's not at if after the second turn it's still not at door 1, there has to be a door 2. And for B, 1, 1, 5, 5, 3 works. Because like it just imagine for uh any single time like where the items at it does not escape both sides. And so the last time where it's picked, it has to be at 3. Otherwise it would pick earlier. Okay, this question is pretty long, but again, you can kind of notice this pattern that this is always a generalization of this one. So uh to simplify it, I'll just go through like what VII is. So for VIA, you pick like 1, 1, 5, 5, 9, 9, 13, 13, and then you pick 3, 7, 11. And so you generalize it, you get like 4L plus 1, 4L plus 1, 4K plus 1, and then 3, 7, 4L plus 3, and then 4K plus 1. And same idea as before, you group it into like A1, A2, A3, A4, A5, A6, A7, A8, A9, A10. So you interchange between groups of 1 and groups of 3, and you realize that you can get at least 2 items from each of these groups of 3. So it's like at least 2, at least 2. And then you can also pick up all the items behind the doors that are like having a multiple of or having a remainder of 3 when divided by 4. And so you add up every one together with the number of groups that you can guarantee at least 2k plus 2 items. Okay, therefore n equals to 6. Okay, basically the host this have a way to prevent Elise from winning everything for the 6 items. And um so if Elise like picks either door 1 or 2, then the host can swap the items behind door 1 and 2. And also for door 5 and 6. And for like the times where Elise has like picked the door 3 and 4, so the host can like prevent Elise from getting item 4. And then same thing when Elise tries to pick item 4, the host can prevent Elise from like picking item 3. And so Elise can like so basically the host can always guarantee that A4 is behind the door that Elise don't pick. And you realize that why, like, for the other previous cases, this does not occur is basically because of its parity. Yeah. Okay, and that's the end of MAP 2022. And hope you enjoy. See you soon.